So now let's start. Basically, let's continue where we left last time. So basically, remember we started the cost minimization problem, right? But initially we said that, okay, firm's objective is to maximize profits, right? So this is kind of a recall. So we said that firm's objective is to maximize profits, but we said that profits are total revenue minus total cost, but we said that this portion, so this is P times Q, of course, if the firm is a price taker, we said that does not necessarily the case, okay? And minus, so we have the total cost. You said the hocam, or if they're using only labor and capital, so it's wage times L minus R times K, right? So here we actually said that, so this is sort of the total cost. And then we said that, well, for the time being, we are not going to deal with this portion because, you know, how the firm is actually deciding on the quantity, how much they would like to produce or how much they would like to sell. But instead, we're going to assume that firm would like to produce, let's say, Q0 amount. And then we will try to find, in order to produce this Q0 amount, what is the minimal cost, right? So if you want to use labor and capital, and if you want to produce this Q0 amount, what is the minimal cost? So we said that this is kind of and we said that this is going to be the cost minimization problem that you're going to solve. So that's basically minimize wage times L, R times K, subject to, actually you would say F of LK, right, equals to Q0. So basically you want to produce a certain amount, but the cost you would like to minimize, you would like to find the optimal K and L, which is going to minimize the cost of producing that amount, right? So that's what we said. And from here, when you solve this problem, how did we call the input demands that we got? They were called what? Do you remember? We called them again, you know, because it's a minimization. Remember expenditure minimization? Again, it was like C, XC, and YC, but there they were called compensated, right? Demands. Here we had L to the power, right? LC, we called it. And this was a function of what? Wage R and Q0, and KC, wage R and Q0, okay? And how did we call these guys? We called them conditional input demands, right? So these were called conditional input demands, okay? And then remember, when we plug these guys back into our objective function, then we said we get our value function. And the value function that we get, we said that we're going to call it cost function or total cost function, whatever. And then this would also be a function of wage R, this Q0, which is going to be wage times LC, wage R Q0, plus R times KC, wage R Q0, okay? So this is basically the case. So that's what we said. Now, so this is actually the cost function, right? We called it. So this is called cost function. Fine. And then remember during our last class, this is how we basically ended up, and I asked you a question if you remembered. So I said that this is, so let's actually draw a cost function. And for instance, one case, and then remember we defined, this was the cost function, and then we defined the average cost, right? So we had average cost, wage R Q0, which was the cost function divided by, so I'm going to get rid of these Q0. You understood. It means that for a given level of Q, but it can be any Q, okay? You can call it Q bar or you can leave it as Q. So this is going to be the average cost. And then we had the marginal cost, wage RQ. This was what? Marginal cost was the derivative of the total cost function, right? So basically del C wage RQ del Q, okay? So this is basically the case. Now, so these were the average cost and the marginal costs that we talked about. And then I drew something like this, right? So I said that, okay, so let me draw a total cost function or cost function. I put here Q. I have something like this. And then I also draw the marginal cost. So here you told me, Hocam, here this total cost function is something like this. It's A times Q, right? So it's some constant times Q. It goes through the origin. And then it is something like this. And then here I put marginal cost, average cost. And you told me, Hocam, what is marginal cost? What is average cost? You said it is, right, constant. So it's basically A, for instance, right? So it's something like this. And then we actually said that, so this total cost is coming from what kind of a, remember, so because this cost function is coming from the solution to this problem, right? So obviously it will depend on this production function, right? So now then we said that this is coming from what type of a production function? Remember I said that, let's think. We said Cobb-Douglas, or it's actually a little bit more specific than Cobb-Douglas. So this is coming from
Constant returns to scale.
So we said, remember, constant returns to scale. So this is actually, this type of a cost function is basically coming from, should come from a constant returns to scale production function. Why? So whenever you need to figure these kind of things out, so you can always think of it like this. Okay, I know cost function should be the solution to that problem, right? So it should be basically the solution to that problem is LC, KC. It's the value function of that problem. So when I put those optimal values back in there, that's my cost function. Now let me try to think. So suppose, let's say that I want to produce, okay, suppose 1 unit, let's say, okay, so wage RQ is equal to 1. Suppose I want to produce 1 unit. And in order to produce 1 unit, let's say that let's say that K1 and L1 are optimal levels. Okay? Suppose, I just assume. Then my cost would be what? If K1 and L1 are optimal levels to produce Q is equal to 1, to produce 1 unit, then what is my cost? If these are optimal levels, wage times, right, L1, R times K1, right? So these guys are optimal. Okay, so to produce 1 unit. Now I need to figure out, now I would like to produce wage R, Q is equal to, let's say, Q bar. Some other 5 units, okay, some other amount. So suppose this is the case. Then, what should I know? In order to, let's just first think of it like this. If there is constant returns to scale, right? So then in order to produce Q bar units, can I produce Q bar units by M times K1, M times L1? If there is constant returns to scale. Right? Because you said that, oh, sorry, no, what is M? You would say, tell me, Hocam, what is M? So it's Q bar, right? So if there is constant returns to scale, and if I want to produce this much, I know that I can use Q bar times K1, Q bar times L1, because I know that in my, if there is constant returns to scale, then I have this, LK, right? So basically TL, TK is T times F of LK. So in order to produce Q times Q bar times, right? So here I'm producing 1. So suppose this was 1. So if I want to produce Q bar, then I can actually have T times Q bar times L, Q bar times K, right? So that we know. Now, we know that, so these guys can produce Q bar units. But the question is, are these guys optimal? So we know that we can produce. So we know that this would be satisfied, but are those amounts optimal? So do you think these are optimal? So now the question is this, whether these guys are optimal. Can produce Q bar units, but are they optimal? How will I know?
But the marginal cost is equal to the average cost, I think.
So remember, what was the optimality condition? What was the optimality condition? So remember, it was, the optimality condition was what? From here, you solve the problem, you get the optimality condition, which was? So which was, right? We said the marginal rate of technical substitution, right? So are they optimal? For them to be optimal, we need to have this. MRTS should be equal to wage over R, right? So here I know that, if these guys are optimal, right, these guys are optimal levels, so then I know that MRTS, right, so let's say it is a function of K1 and L1, right, is equal to wage over R. But what do we know? If there's constant returns to scale, we know what about the marginal rate of technical substitution? It's actually, so we said that when there's constant return scale, you said, hocam, it's homogeneous. And if it's homogeneous, it is homothetic. And what was the characteristic of MRTS being homothetic? It depends only on the ratio, right? So whatever this MRTS, I know that it's going to be, we don't know, but it's like K1, L1, right? So it will only depend on the ratio. So so there is just some function here, which only depends on the ratio. You set it equal to wage R, and then you solve for it, right? Now, in this case, I'm going to have my MRTS, and I'm going to plug my new points, right, new bundle there. Q bar times, let's say, K1, Q bar times K L1. Okay? Wage over R. Do you think these guys satisfy this equation as well? Yes, right? Because these will cancel out, and then we would only be left with the ratio, and we know that then these Q times K1 and Q bar times L1 would satisfy the optimality condition, right? So because MRS, remember, was the same. No matter if it's homothetic, we had something like this. Okay, so this is K, this is L. So it was something like this. All these guys, right, the slopes. So if you have the same wage over R, so I have these guys, so all these optimal points are along a line, right? But remember, these are not, this is K and L, so that's not the cost. So just be careful, okay? So, but we know that this only depends on the ratio, right? So it only, if it's homothetic, it would only depend on the ratio. Then Q bar times L1, Q bar times K1 would be the optimal point, okay? So that's why we know that, are they optimal? Yes. Now the question is, they are optimal, okay? So they are optimal, and then therefore, what is the new cost? If the new optimal points in order to produce Q bar are Q bar times K1, Q bar times L1. What is the cost? Wage times, right? Then you write, oh, hocam, it's not easy. It's wage times, right? Q bar times L1 plus R times Q bar times K1, right? So this is basically the case. Now what happened? So this is basically, so this is what we have here. And so here you can actually say that Q bar, right, in Q bar parentheses, wage times L1, R times K1, okay? What was this? This is the cost of producing a single unit, right? So this was basically, so this is, you see, Q bar times C wage R, where Q is equal to 1. So basically what you need to see is that you see that the total cost function is whatever this guy called this A. It's A times some constant times how much you would like to produce, okay? So you see that's why when there's constant returns to scale, we have this sort of a cost function. So you see it's not that immediate to see. You have to do some arguments, okay? But I hope it's clear, okay? Now we figured A. So now we know what A is, right? So apparently A is cost, or you can call it total cost, doesn't matter, of producing wage R, Q is equal to 1, right? So we know what this coefficient is as well, okay? So you see that apparently this type of total cost function would come from constant returns to scale. But what happens is that mostly, both in production functions and also in basically hence in the cost functions, we would see all of them, okay? So we would have production functions which are exhibiting both for some quantity levels, increasing returns to scale, for some quantity levels, constant returns to scale, for some quantity levels, decreasing returns to scale, okay? And hence, the cost function would be showing all three of them, okay? So now let's actually have a look at that. So the more general total cost functions you would see is this. So let's call it like the second type. So that was a very special case with constant returns to scale. But usually we would have total cost functions like this. So here I have total cost, here I have my Q, okay? And usually we would have something like this, okay? So this is going to be the total cost. So it would have this cubic shape mostly, okay? And then here it's marginal cost, average cost, and here it's Q, okay? Now let's try to figure this out. So what's happening? If I want to draw the marginal cost, okay? So what's happening here? So marginal cost, remember, was the derivative of total cost with respect to Q. So when I take the derivative of this function with respect to Q, what's happening here? It's what? The derivative of this function with respect to Q is the slopes, right? So it's, as you said, what's happening to the slopes? They are decreasing, right? So basically marginal cost is decreasing until where? Inflection point, right? Until, so inflection point, let's say it's somewhere here. So here you see that these slopes are decreasing. And then, so we call this point, so this is basically the inflection point, okay? So you can actually say A. So A is the inflection point, okay? Now, so this is the case. So here, let's put it, so let's call it, if you want, Q prime, okay? Now, then you would say that, hocam, marginal cost is going to be decreasing until the inflection point, right? And then what's happening to the slopes? What's happening after the inflection point? What's happening to the slopes? They are increasing, right? So basically, sometimes there might be a flat portion of this where it's linear, okay? So where the slopes are, they're not changing, right, at some point. So they are actually constant. So you can have some flat portion if you want, you know, there. But so basically what you have is that afterwards the slopes are increasing, right? So this is the marginal cost. Now if I want to draw the average cost, what should I do? Average cost is what? Average cost is like cost divided by Q, right? So we have it here. Cost divided by Q. So how can we show average cost on the graph? So if you have, you see, if you have these guys, you see these would be average cost because this is total cost divided by Q, right? So the, you know, like the, basically the tangent there, right? It's going to be, so we have this divided by this, right? So basically, so these are actually the average costs, right? So if you look, what's happening to the average costs? They are decreasing until which point? So average costs are decreasing until the inflection point or? Basically, actually they are going to be decreasing until where? Where it is? Where do they have the same slope? When these guys are tangent to each other, right? Maybe somewhere here, okay? So the slope of this guy and this guy are the same, okay? So it's not the inflection point. Inflection point is important for the derivative, right? But it's here, it's actually this divided by this, right? This divided by this. As you said, hocam, it's decreasing, but until this point, right? So this is Q double prime. So here I have Q double prime, okay? Then you said that, hocam, then how shall I draw my average cost curve? Remember our discussion with the average product and marginal product. So in order to draw averages and marginals, remember there was this relationship between them. What was it? When marginal is above or when marginal is below the average, what's happening to the average? Decreasing. And you said that, hocam, until here it's decreasing, right? So if average is decreasing, where should I draw? Shall I draw it here or here? Above or below? Above, right? Because average should be here. So you should say that, oh, hocam, it should be something like this until this point, right? And then afterwards we said that average is increasing, right? So you see it's important because, and remember what did we say about the average product and marginal product? Average and marginal are equal to each other where? When they're equal to each other when they intersect, right? But what is the characteristic of that point? It's where the average, for instance, here is at its minimum. And remember for average product and marginal product, it was where average was at its maximum, right? So it was basically the case. So mostly we would see a case like this, okay? And then we would actually see, so it's going to be something like that, and the marginal cost and the average cost would look like this, okay? And then this is going to be, so we said that on this portion, whenever you have an average cost curve like this, okay, so this is, let's say, average cost and Q. So we actually say that you have in this portion what? So where average costs are decreasing, we say you have increasing returns to scale, okay? So remember this, you guys figured this out. You said that, hocam, when average cost is flat, we have constant returns to scale, right? So when costs are decreasing, basically it means that in order to produce Q, you increase your labor and capital, but they pay off more than proportionately, right, to you. So they're going to bring you more Q than, you know, like let's say you double capital and labor, but they bring you more than double the output. So when you divide right by Q in terms of the average cost would be decreasing, right? So we have IRS here, we have constant returns to scale here, and in this portion we have decreasing returns to scale, okay? So you can figure this out by looking at the average cost, or as you can see, then you would say that, hocam, here, where the average cost is kind of decreasing, we are going to have, right, increasing returns to scale at some point, and then we're going to have the constant return scale, and then we're going to have the decreasing returns to scale, okay? So you can figure this out. For a production function, basically, this is going to be the case, okay? So if you have a production function, suppose you have this, where you basically, if you put Q here, so it's different, but don't worry about it, but it's, don't worry about that. It's going to be, think of it like this. So mostly, it's much easier to detect it from these guys, okay? If you have a production function, just to keep in mind, it would be something like this. So if you put Q here, and suppose you have a production, you want to show your production function with respect to Q, here, because we do it for a given Q, but for a Q, then it would be the total product. It's called the total product curve. And it would look like, so for instance, you have labor here, because we cannot, remember, production function is going to be it's going to be a three-dimensional object, right? So we have K and we have L. So if you have this, then it's going to be the total product for L. There might be some portion where the returns are actually increasing. There might be some portion where the returns are decreasing. So you would have something like this. Okay? But don't worry about it. Okay? So this is the total product curve, but this is the cost. Here you see when you increase your labor, the contribution to Q, basically this is Q, is actually, right? So at some point, but then it starts decreasing, okay? So this is the production technology which lies actually behind this cost function, okay? But don't worry about it. So mostly we can detect everything from here, okay? Now, this is basically the case. Now we see that most probably the cost functions are like this, and maybe you haven't written it, so let's keep it up, okay? So it's something like this, and again, if I want to show, remember the fact that the relationship between the average and the marginal, how can I show that? The average cost and the marginal cost. How am I going to show mathematically that when one is above the others, one is decreasing, and they cut each other at averages minimum, blah, blah. So how do we show it? How did we show it for the marginal products? You just use math, right? In order to show that they intersect at their minimum, what do? You should take the derivative and set it equal to 0, right? So basically, so here's what we have. So the average cost is, we know it's this, wage RQ divided by Q. Now I'm going to take this guy's derivative with respect to Q, okay? Okay, so let me take this. It's del C del Q times Q minus C times 1, derivative of this guy, divided by Q squared. Right? I didn't do anything. I just took the derivative of the average cost. So del average cost del Q, right? Now what is this? So C times 1. Now if I take it into 1 over Q parenthesis, then this is del C del Q, right? Minus C divided by Q. And suppose Q is not equal to 0, then what do I have here? What is this guy? Marginal cost, right? What is this guy? Average cost. Now you see from here, right? When marginal is equal to average, this is going to be, so when marginal cost is equal to average cost, we know that average, this is going to be 0, right? Which means that average is at its minimum, right? Cost is at its minimum. So that's, we know. And when marginal is above the average, what's happening to the average cost? And this is greater than this guy would be greater than 0, which means that average cost is when the derivative of average cost is positive, which it means that average cost is increasing, right? So average cost is increasing, okay? And then the third one, you see that when marginal cost is less than average cost is decreasing, okay? Then it's going to be less than 0, which means that average cost is decreasing, okay? So you see that, I mean, we know this fact graphically and intuitively, but now we can always show it mathematically, okay? So which is easy, okay? Now, let me erase this guy. There was actually a nice property in the expenditure function when you have the expenditure minimization, like problem. We had a nice property of the expenditure function. When we take, do you remember? So remember the expenditure minimization problem. So recall, let's say. So in expenditure minimization problem, remember the value function here was the expenditure function. And we had this nice property. What was this? Expenditure function was a function of what? Prices and utility, right? The level that you would like to achieve, Px, Py, U bar. So when you take this guy's derivative with respect to Px, what were we getting? Compensated demand for x, right? So we were getting xc, Px, Py, U bar. And we called it what? This was called Shepard's lemma, right? So here we had, remember the Shepard's lemma. Shepard's lemma was this. Basically, you take the derivative of the value function with respect to one of the parameters, and then it's going to give you this compensated demand. This was an application of which theorem? Envelope theorem, right? So it's a much more general result than this. Now, because remember this envelope theorem is a much more general result than this, so here, if you make the analogy, what can we say about the cost minimization problem then? If you think of the cost minimization problem, what would you tell me? So what is remember expenditure function was the value function. What is the value function in the cost minimization problem? Cost function, right? So basically I have my cost function, wage RQ. This says that take the derivative of the cost function with respect to wage. This is going to give you what? LC, right? Conditional input demands. LC, which is a function of wage RQ, okay? Again, because it was an application of the envelope theorem, we can again apply the envelope theorem to the cost minimization problem and get a similar result, okay? So we would have another Shepard's lemma here, which is this. And also we can have this, right? Wage RQ, del R, KC, wage RQ, okay? See, so it's very, as you said, here's the analogy, and we can show it in very similar ways, okay? So this is so if you're given the cost function, you can always take the derivative with respect to wage and with respect to R, and then you would get these conditional input demands, okay? So which is the case. Now let me write down the properties of the cost function, okay? Remember we have written these down for the expenditure function, and now we're going to write them down for the cost function. They would be very similar. So the way we argue about them would be very similar as well, okay? So let's write this. Properties of cost functions, okay? So basically we have these properties of cost functions. So the first property is this. Cost functions are, now you guys, homogeneous of degree what in input prices. What does this mean? Homogeneous of degree what in input prices? It means that, so think of your cost function. I have my cost function wage RQ. Apparently it says homogeneous of degree something in these prices, we'll see. So it says that T times these guys, apparently it's going to go out T times C wage RQ. Guess if this is like this, then? So we're wondering what this is, right? So you said that hocam it should be 1. Why? Again, so this one, and remember the sort of the analogy, the argument basically that we made for the constant returns to scale and such. Remember we said that, oh, if this point is optimal, then T times these K1, L1 is also optimal. Remember we were making some arguments like that. Again, here we might need to make these kind of arguments. What does this mean? Homogeneous of degree 1 in input prices, but why? Why? Why is this the case? Again, I have to, like make an argument, right? I have to think. So let's actually think, what does this mean? So let me ask you this question, okay? So basically I have to show that so let's think of it like this. When prices are wage and R, suppose, right? So the price level is given to you as wage and R. Suppose you have, again, L1 and K1 as optimal points. Fine. So suppose these guys are optimal points, okay? Now, so basically you can say it wage RQ, K1 is wage RQ, okay? Suppose these are optimal points. Then what is my cost? When I have this, my total cost wage RQ is wage times L1, as you said, R times K1, okay? Now my prices are, instead of this, now I have T times wage, T times R. What are my optimal points? Now you have to argue. You have to think that, okay, so is this L1, K1 still optimal? Do you think they're still optimal? Would you, when prices are T times W, T times R, are you going to, and suppose you would like to produce Q bar level, both here and now with the new prices, are you going to change your optimal bundle? Yes? Again, what is the optimality condition? Remember, here, optimality condition is MRTS equals to wage over R, right? Now, initially, this was the case. Now I have T times wage, T times R. Did anything change? So these guys cancel out if, right, if L1 and K1 was satisfying this, right? When things are TW, TR, they are also going to satisfy this equation again, right? Because the ratio of the prices, it didn't change, right? What matters for us is the ratio. But what you were saying, yes, because now costs are higher though, right? It's the same optimal bundle, yes, but now the costs are much higher, right? So we said now we have TW, TR. Then we know that it's the optimality condition, because where would you switch? If labor is relatively, let's say now, suppose labor, the price of labor doubles, but the price of capital wouldn't change, you would switch, right, to capital. But here, they both increase. Like think of the case, right, where both of the prices increase, right? When you consume some good. Are you going to change your optimal bundle? Okay, so, or let's put it like this. There you would change. But here in this condition, or for instance, let's put it like this. Suppose prices double. Think of the expenditure minimization problem. Suppose prices double and you want to achieve exactly the same level of utility. What's going to happen to your, are you going to change your optimal bundle? If you want to achieve the same utility level and prices double.
If the utility based on the quantity, we shouldn't change our...
So you wouldn't, but your expenditure would increase. So your income should increase, definitely, right? The minimal amount of expenditure in order to achieve this utility level would be now, with those new prices, would be higher, right? So similar here. So now I have TW, TR, but the price ratio didn't change. So basically, as we wrote down here, if L1, K1 was satisfying this, then they're going to satisfy this one as well, right? Because there's no change in the price ratios. So therefore, you can say L1, K1 are still optimal. So basically, you can say this, L1, T times W, T times RQ, K1, T times W, T times RQ, equals to L1 wage RQ, equals to K1 wage RQ, okay? Remember, the derivatives were usually, if the function itself is basically homogeneous of degree 1, their derivatives were homogeneous of degree 0, right? So you can see all those mathematical facts that we have said here. But you see that these guys, they are still optimal, okay? These guys are still optimal. Then what is the total cost? So here in this case, total cost T times W, T times RQ. Then total cost is what? T times W times L1, right? T times R times K1. And you see it's T times wage times L1, R times K1, which is nothing but the cost, right? Before, when we basically saw it was actually the total cost, right? When we have wage and R as prices, okay? So basically, so you see that when these guys both multiplied by T, the optimal cost is also multiplied by T, okay? So that's why it's homogeneous of degree 1 in input prices, okay? You see, it's not that immediate, but did you understand the logic, right? Because the price ratio didn't change. And for us, what matters, what determines the optimal point is the price ratio, right? So that's why, okay? Now, we basically have another property. So let me write it down, the second one. So we have total cost functions are, okay, so are non-decreasing in Q, wage, and R, okay? What does that mean? If I want to show a function is non-decreasing, what should I do? I should show constant. So if it's non-decreasing, so basically I should, if I want to show a function is increasing, decreasing, non-increasing, right? So you should take the derivative. So basically you take the derivative of the cost function, wage RQ. It says that when you take the derivative with respect to wage, what is this? We just said it. When you take the derivative of the cost function with respect to wage, what is it? It is conditional labor demand, right? So it's basically LC, right? Wage RQ. And we know that this should be positive, right? We cannot think of negative numbers, right? Because it's labor demand. So here we have wage RQ, del R. This is going to be KC, as you guys know. Okay? And what about this? Wage RQ, del Q. What is this? What is this? It's called? What is the derivative of the cost function with respect to Q? Marginal cost, right? So it's actually the margin of 1, 0. Marginal cost, right? So this is basically, and can marginal cost be negative? Does it make any sense? What does it mean? Remember, always go back to the definition. It means that I produce another unit and it doesn't bring me additional cost, but it even decreases my cost, right? So it's very good, but unfortunately that doesn't happen, right? So marginal cost is also positive. Okay, so that's how we actually say that these guys are non-decreasing in wage, Q, and R, okay? And then there's another one, the last one, and you can check, these are very similar to the properties we mentioned about the expenditure function, okay? In input prices, okay? So apparently they are concave. And remember, for the expenditure function, in order to show that they're concave, we had this kind of an argument. So these are not formal proofs, but we argue. Okay, we have all the intuition there. So I put total cost here, and I put basically wage here, okay? Because it says that concave in input prices. Fine. So suppose when wage is wage prime, suppose we did the cost minimization problem, we solved it, and we found the cost, okay? And suppose it is something like this, cost, wage prime, R, Q, okay? In order to produce that much. Suppose this is this. And suppose when prices are wage, and let's say R, the optimal amount of labor is L1, okay? Now suppose price of labor increases to wage double prime, okay? So if I want to consume, so let's say L1, K1, okay? So suppose this is wage double prime and this is R. Suppose I want to use, as the firm, I want to hire the same amount of labor and same amount of capital. What's going to happen to my total cost? So here my total cost was, let's say, wage prime times L1, R times K1. And here, suppose I would like to hire the same amount of labor and capital. What's going to be my total cost? So let's call it total cost tilde. It would be wage double prime, right, times L1, R times K1, right? So how is my total cost increasing? If I keep consuming the same bundle, it's going to increase. So this is just increase, right? This part stays the same. This part increases. It is? In a linear fashion, right? It's going to increase, right? Suppose this is, now this was 1, this is 2. Then it's going to be, right? In terms of L1, it would be linear. 1, 2, 3, 4, it would be. So if you keep on consuming the same bundle, you would have something like this. Okay, you would have, it would be linear, right? So let's put it like this. So let's say cost if you don't optimize. Okay, because we want to produce Q. You know that with these guys you can produce Q. But now the price is higher. You can actually optimize, but suppose you don't do it. Then it would be linear. But we know that you can do better than this, right? When price of labor is higher, then you would re-optimize, and probably it's going to be something like this, right? This is what we said about the expenditure function. You'll definitely do better than that. Worst case, you would have this much. You keep consuming the same bundle, you don't change your optimal bundle, but we know that you can do better, right? You can do better than this. That's why the real cost function, C, that's what we said, wage, RQ, in general, it would be like this, okay? So whenever wage changes, you re-optimize all the time, okay? So that's why it's concave. A concave function is when you have, like any line above, so any tangent concave function, remember we said that any tangent line should stay above the curve, right? So this is how we argue here, okay? Again, it's not the full proof, but you have the intuition, okay? So these are the properties. But I think towards the end of the previous class, one of your friends, he asked me this, and he was right. He said that, hocam, when you draw this total cost function, you started from here. So when I draw the total cost function, whether it's constant returns to scale, increasing, decreasing, returns to scale, whatever, you draw it like this. You start from here. Why did I do that?
Because you didn't include fixed cost.
I didn't include fixed cost?
No,
Really?
maybe.
Was it 0? So what does this total cost was something like this. Wage times L, C, R times KC.
We assume all the other costs are equal.
If you don't produce, there's no cost.
So why it's, so there is the cost of capital, right? Definitely. There is the cost of labor. And remember, I only have 2 inputs. So why did I start from there? Do we have fixed cost here? No. Why don't we have fixed cost? Because the firm is deciding on what? Both the amount of labor and capital. And there are 2 inputs. Fixed cost is there when?
Then you cannot change it.
One of them, right? So when at least one of your inputs is fixed, it has to be fixed, and mostly it's capital, we'll see, then there is fixed cost. But what does this tell us? We have fixed cost when?
Sure.
In the short run, right? So from now on, know that the problem that we solved, because the firm is deciding on optimal amount of capital and labor, this is actually a long run problem, okay? So this was the cost function that we have got here is the long run total cost, because we decide on both of the inputs, okay? So for our friends who haven't taken an econ course before, we have this very important distinction. We didn't have this in consumer theory, but in firm theory, it's pretty important, okay? That we have to make this distinction between the time periods. You might have a short run, right? There might be, the time period might be referring to the short run or long run. But we don't have, we don't say that, 1 month is short run and 6 months is long run, okay? It depends on the situation, it depends on the context, okay? But it is very important, okay? And how we define them is, we said short run is a period, refers to a time period where at least one of firm's inputs is fixed. So a firm is not that flexible. It cannot change everything, okay? So suppose you're Mozart Cafe. You would like to triple your production. Can you do it in an hour? No, right? Because, you need maybe more, or maybe you might not even do it in 1 day, right? You might need more ovens. You might want to have, like more chairs, more tables, right? You want to serve more people. So it might not be possible, right? So for maybe 1 month, maybe in 6 months they can do it, maybe in 2 months they can do it. But for instance, just a week is short run for Mozart Cafe, okay? But I'm sure they can do it if they have 6 months, right? Maybe even less than 6 months, okay? So it's very important to make this distinction between short run and long run. So in short run, firms are not perfect, they're not flexible, fully flexible, okay? They might have some fixed input. That's when we're going to have a total cost function, which is going to start somewhere from here, right? But the one that we have cost minimization problem, that we have solved is actually referring to the long run. Okay? So that's very important. Keep this in your mind. So let me write this. So short run refers to a time period, okay, during which firms have limited flexibility. Okay? So, and here long run refers to a time period firms during which firms have more flexibility. Okay? So this is basically the case. So what we assume is that in our case, mostly in the short run, we keep, and this flexibility is also, for instance, you can think of it in terms of technology as well. In the long run, firms' technology might change. But in the short run, firms' technology, production technology is also fixed. Okay? So here, but mostly what we do, this is the typical practice because it's much easier to hire laborers, but it's harder to have capital, right? Physical capital. That's why we usually say, we assume most of the time, okay, in short run, capital is fixed. Okay, so this is basically one of the inputs is fixed, and mostly this is actually capital. Okay, so when capital is fixed, how would my production function look like? My short run production function. Remember, my production function was something like this. If capital is fixed, let's say at a rate k bar, this is going to be my production function, right? So k is given, so I can only change L. That's all I can do, okay? So this is basically the case. The firm can only vary labor. Then if you would like to think of the short run total cost, what is the short run total cost? It's going to be wage times L, whatever the optimal amount of L, plus R times K bar, right? So you see that R is given to me. Level of capital is also fixed, given to me. So this part is what we call the fixed cost, right? So it's in the short run, as we said, because in the long run, we can decide on K. But in the short run, we're fixed. I'm Tadım Pizza. I only have this restaurant. I only have this many ovens, pizza ovens. I only have this many tables, chairs, whatever. And for at least for some certain period of time, my capital is fixed. Okay? So this is fixed cost. And this is what we call the variable cost. Okay? Because you can vary. It's going to vary. Okay? So that's the fixed cost, and it's the variable cost, okay? So if you want to write down short run total cost, okay, or your book calls it SC, short run cost, okay? So this is going to be a function of what? You guys tell me. Wage, R, Q, and this time, right, different from this guy, here we had the total cost function, which was a function of wage RQ, but now I have to also incorporate the fact that I don't choose K, it's given, okay? So this is the short run total cost function, okay? Now, do you think when I have the short run total cost, is this all, remember this guy was the minimal cost, right, to produce that quantity. Suppose I give you this short run total cost function. Do you think it's going to be the minimal quantity to achieve, do you think it's going to be the minimal cost to produce that quantity? No? Yes? Maybe? Okay, so let me ask you, Suppose you want to produce a given level of output, so short run, right, total cost, wage, R, Q, K bar. I gave you this function. Can you say that this is the minimal cost in order to produce that Q? I know that the cost function was that, right? So this guy, the long run, the total cost function, or I call it C, okay, C wage RQ, or total cost wage RQ. This was long run. So I know that in order to produce any quantity Q, this is the minimal cost. What about this guy? No? Okay, so let's do this. So the answer is no, but only for one point it's going to be the minimal cost. For which point?
Yeah,
Then the
K.
cost is 0.
When the quantity is 0?
When the
No.
optimal K is.
So if this K, if you pick the quantity, you just, miraculously, you pick the quantity where this K is the optimal K. You solve the cost minimization problem for some quantity level, let's say Q1, okay? And suppose the optimal K is K1, right? You solved it. And you pick that, and in your short run total cost function, and this is your level of capital, okay? If you pick that quantity where this K1 is the optimal in the long run, right, when you solve the cost minimization problem, then only at that point it's going to give you the minimal cost. But other than that, it's going to give you higher costs, okay? So let me draw this. So let's put it like this. So you'll understand maybe here much better, okay? And then we'll stop. So this is K, this is L. So I have this. So we know that suppose this is my total cost, right, line. So minus wage over R, we know that slope is this, okay? And then this is going to be the optimal amount. So let's say this is K bar, and let's call this L1, okay? So you see that this is, I did the cost minimization problem, I solved the cost minimization problem, and then, so this was my quantity that I wanted to produce, let's say Q0, let's call it Q1, okay? And this was the optimal amount of capital, and this was the optimal amount of labor. So let's call it K1, I'm going to call this K bar. Suppose now my capital is fixed at this level, okay? Now it's going to be like this. Okay? And I have some other curves, right? I want to produce other quantities, fine. Suppose I have one here, Q0. Suppose I have one here, Q2. In the short run, in order to produce Q0, right? How much labor do I need? How will I find it? In the short run? Right? Because your capital is fixed at K bar, right? So your capital, unfortunately, my production technology says that if your K bar is this, and if you want to produce Q0, you have to be here, right? Let's call it L0, okay? But this is in the short run. But if my capital was not fixed, where would I be? I would be at a point, right? Because suppose I wanted to produce Q1. Now I want to produce Q0, and I can choose my capital and labor freely. Where would I be? Right? You would say that, oh, hocam, this is the total cost 1 curve, so wage over R, so it should be, you would probably be somewhere here, right? You would be parallel to this guy, and you would probably pick a point here, okay? So what's happening? So let's call this E1, let's call this E0. These are the long run optimal points, right? These are the optimal points. What's happening here at E0? So what's happening here? You are using too much capital or right? Too much capital or too little capital? Too much, right? If you fix, so apparently if you want to produce Q0, you don't need to have this much capital, right? You can have lesser costs, you can use less capital and a little bit more labor, right? Where your costs would be much, right? This is TC1, much lower, right? Your costs would be much, much lower. You can achieve that, but if your capital is fixed, you cannot, okay, achieve that. So basically you see, so let's say to produce Q0, okay, K bar is too much. You're using, but because suppose you opened up Tadım Pizza, but you're not selling, you're not producing that many. Tadım Pizza is a pizza place, okay, so it's nice. So you guys ate, right? So we ate it. But remember, so it's basically, right, so it's the pizza place. Suppose you open up this big restaurant and such, now your, you know, like capital is fixed, but you're not producing that much. So apparently that restaurant was too big to begin with, let's say, okay? So K bar is too much, but in the short run, there's nothing you can do, okay? Or you can think of it, for instance, if you want to produce Q2, it's going to be here. So let's put it L2, okay? You need this much labor. And of course, that's the amount of capital, it's fixed, okay? So you see that this is L2, so, but is this, if you could optimize, you wouldn't pick this point, right? If you could optimize, you would probably be here. So let's call it E2, right? So let's say to produce Q2, K bar is too little, right? And we know that to produce Q1, K bar is just enough, right? Is the optimal amount. Okay? So you see, this is the problem. That's why that is the that's the problem. So basically, it's going to be E0, and the total cost curve that is going through this guy would be this. Whereas you could do, the total cost that you have could be lower, okay? So you can think that this blue line is going to be the short run total cost, okay? Which is higher than the long run total cost to produce Q0 units, okay? So the long run total cost, right? Long run cost to produce Q0 units, the minimal cost is actually this much. Okay? But because you're in the short run and your capital is fixed, you see your cost is the blue one, okay? It's higher, okay? And similarly, you can say the same thing for Q2, okay? So this is the problem. You see that short run cost curves, after this we can say that they are always above long run cost curves, okay? Long run, for instance, total cost curves. But just at one point, they would be equal to each other, okay? And that is the point where K is the optimal amount, optimal K, for that quantity, okay? For just one quantity, that's going to be the case, okay? So let's continue in our next class, okay?